Okay, so do you want to describe that lesson?
Yeah, good afternoon. Today's lesson is going to be on Newton's second law, or force equals mass times acceleration. And I'm going to have the kids move a cart on a ramp to investigate how the cart moves when you apply a different type of force to it. So we're going to revisit Newton's first law on dynamic equilibrium, and then we're going to move into resultant forces or net forces that actually cause acceleration. We're going to learn a little bit about friction. We're going to learn about weight versus mass. The class that I teach is grade 10 physics in preparation for AP physics. And today I'll have to wear a mask because there are COVID restrictions in place in our school. So I hope you enjoy what you're about to watch. Thank you. Test, retake / makeup, depending on who you are, will be on Wednesday during class. So we'll find out, see how you guys are doing. Okay? All right, any questions before we begin? You guys are pretty straight up with that? Okay, well, today we're going to begin Newton's second law. We did Newton's first law. What was the definition of Newton's first law? Jim? Do you remember Newton's first law? Remember about stationary object versus the moving object. So there's static, and then there's also dynamic, right? Static and dynamic equilibrium. So the big term for Newton's first law was equilibrium. Ian, can you help out, Jim?
Oh, so an object that's not at rest will stay in rest, and if it has like a constant velocity, then it'll stay in constant velocity in speed.
Unless
non-net zero forces applied to it.
Okay, unless an outside force is applied to it to change its state of motion or rest, right? That's called disequilibrium, or it's not in equilibrium. Okay, so we were focused on objects in equilibrium for Newton's first law. Now we're going to look at objects that are not in equilibrium that have what we call a net force. So we're going to look at that a little bit closer today. So we're going to look at Newton's second law. Now, on your table, I have a ramp and I have a car. And here's what I want you to do with this. Okay, the car has a scale on it. This is a spring scale that we used in the walking the plank lab. You should recognize it, right? It's up to 10 newtons. Okay, and let's remember what newtons means. So what I want to do is I want to write the equation for Newton's second law on the board. We've already seen this equation. Okay? We know what a force is. A force is mass in kilograms times acceleration in meters per second squared. These units come together to form force. And when you have kilograms and meters per second squared, that is a newton. Okay? So this scale on this car is measuring the kilograms times the acceleration of the object. Now, here's the interesting part of this little setup. The car is on a ramp. So if you don't mind, and can I get you to move out of the way for a second? I'm going to have you guys simulate a couple things on your ramp. You can come back over in a second. Okay, so the car is going to be on a ramp, and you're going to hold it here, and you're going to see what it says for newtons. Okay, and I want you to first get a measurement of newtons as it has held still. Then I want you to, so this is static equilibrium. Then I want you to do dynamic equilibrium, which means you're going to move the car at constant speed. Okay, and I want you to compare the newtons on there. After you do that, I want you to add some weight to the car. I want you to add the big weight and the second biggest weight. Add them to the car and then do the same thing. Hold it here. And then I want you to pull it at constant velocity up the ramp and look at the newtons. And then let's talk about that for a second. Okay, so with your partners, with a few people at your table, let's do that right now. Write down the numbers for the 4 scenarios. Again, stationary car, no weights, constant velocity, no weights, and then stationary weights, constant velocity, weights. Okay? Do that right now. Write the numbers down. I'll walk around and discuss it with you, and then we're going to talk about this and look at this, and then we're going to go into something called, we're not going to have equilibrium. We're going to actually move the car with acceleration and see what the difference is. Okay, so do that right now. Go ahead at your tables. Write down the 4 numbers. Okay, on your piece of paper, on your notepads. Okay, so stationary. You might not see anything for stationary. The car is very light. There's one that we're going to talk about briefly today, and it slows things down when 2 objects are rubbing together. Friction, thank you. So friction goes this way. That's the force of friction. And then there's another force on this car, and that is the force of the movement of the car down the ramp. And it's this way. Okay. This is the force of the movement. So now we have 4 vectors on this car. And by the way, because you're holding it up using the spring scale, because you're holding it like this, it's not going down. So you have another force on this car. But if I release it, if I release this spring scale, what's going to happen to the car? It's going to go down. Thank you, Anika, you're going to have to catch it. Okay? It's going to go right down because of gravity. There's a net force on the car that causes it to accelerate. Okay? So, to get this car to accelerate, you need a net force on it. Even with the weights, and I know that Anika said it took 1 Newton for this to go up. If I got it to accelerate up this ramp, it's going to take more than, I'm going to make it accelerate, that's like 1.5 newtons to make it accelerate up the ramp. I need a net force on it to move it. Okay, this is going to segue us to Newton's second law. Okay, and I'm going to give you the definition of Newton's second law. We're also going to look at weight versus mass today. And we're going to look at friction. So there's a few things we have to talk about. You're going to draw a couple more things in your book here in just a second. Okay? All right, let's look at this PowerPoint really quickly. We've got mass and weight. We've got Newton's second law. We're going to actually do an activity today to wrap up the class. It's another PhET simulation, but it's a really good one. They're all good, I think. And this PhET simulation will help you visualize what F equals ma is all about. Okay? All right, so here are the 4 criteria. We've got forces cause acceleration. We just discussed that. You need a net force on an object, and when there's a net force on the object, it's going to accelerate. We're going to talk friction, mass and weight, and Newton's second law. Okay, so in order to accelerate, you need a net force. We know that now. If there's no net force on the object, it's going to be an equilibrium. It's either going to be static, stationary, or it's going to be accelerated. Forces. Here's the scenario I want you to draw right now in your notebook. A rectangular box has 2 people pushing it. One from the south and one from the east. Both pushes are equal in magnitude and are 100 newtons apiece. Draw that box. Draw the 2 people pushing it, but I want top view. You can ignore the normal force and the gravity, or do weight, or the force of weight. I just want a top view of the 2 pushes. And they're both 100 newtons, and they're at right angles from one another. So draw that now. As soon as you have that drawn, ignoring F sub W and F sub M, which is the normal force and weight, I want you to draw the resultant force of those two pushes. I also want the magnitude of the force. How do you find that? And this is a little review. You guys should remember that you're going to need to use, what's that theorem we need to use, Jay? Pythagorean theorem. Okay? It's a very simple operation, nothing difficult. To find that resultant force, you need to use Pythagorean theorem. These are both at right angles, these forces, because you're pushing from the north to the north and you're pushing from the east, okay? All right. What is that resultant force? Anyone have it? Give you another few seconds to figure that out. Yeah, what did you get?
100 times root 2.
What is it?
100 times root 2.
Okay, and what's that simplified?
141.
141 newtons. Okay, here's what it should look like in your notebooks. There's your push from to the north and from the east. So from the south and from the east. This is a rectangular box. And the net force is going to be 141 newtons because the two forces are 100 newtons apiece, and you're going to take the square root of that. Okay, so let's see, where's my eraser? I have it over here. So just a quick review, we kind of covered this last time. If you have a force pushing this way and the other one's at right angles and they're both 100 newtons apiece, you're going to take these two, take the sum of it, square them both, square root it, and you're going to get 141 newtons. Okay, that's Pythagorean's theorem. So that force, that resultant force is 141 newtons. And you guys should have that down. We do not need any angles. It's at 90 degrees. So you should be able to use that pretty easily. Notice that the box is accelerating. It's accelerating to the northwest. Why is it accelerating, Jenny? Why is that box accelerating? This is a fundamental of Newton's second law. Can you help her out, Sophie? Why is the box accelerating to the northwest? It's getting faster and faster. What makes an object accelerate, Ian?
When there's a net force.
When there's a net force. It's just that simple. Please do not forget that. If there is no net force, it cannot accelerate. But if there's a resultant net force on it, it will accelerate. Now I want you guys to draw a rectangular box, but this time I want you to put an individual in the northwest corner pushing against that resultant force. So, you know how that resultant force was leading to the northwest? I guess it would be this way. Well, I want someone pushing against it at 100 newtons. So that person is pushing against this resultant force right here. So you have another individual. You got one individual pushing here, one pushing this way, and now you have one pushing that way. What would be the net force then? Okay? Can you find the exact newtons? And this is going to, we're going to definitely talk about this later on. Would you be able to find the magnitude of that resultant force with all the information I've given you? Okay, give you a minute to draw that, and then we'll talk about it. Okay?
Can they talk about it in, like, groups? Is that possible? Or is that helpful?
Yeah, you can talk about your results in groups if you want to.
Can you give them that instruction?
Yeah. As soon as you're done, see what you guys got.
Oh, wait. Also, like, it moves slower. It moves slower.
Okay, what did we get? Any groups want to share their ideas here right now? The class? We need to talk about friction. What is friction? Okay, friction is that force that slows objects down. Okay, and it occurs when two materials come in contact with one another. In this case, one type of friction is where you have two solid surfaces in contact with one another, and if you look at, get a microscopic image, you'll notice that most surfaces are quite rough. So if I take this chair and I push it across this floor, the floor looks relatively smooth, but it's a little bit bumpy. And I push it across the floor, it's making a lot of noise. There's vibration, and I have to actually apply some force to it to keep it moving at constant velocity. What am I opposing here? I'm opposing friction. To move it, I have to overcome friction. And if it's at constant velocity, my force pushing it forward is equal to the frictional force. The two are the same. Okay? But here's the thing we need to understand. Friction doesn't just happen between solid surfaces. Let's look at this multiple choice question. The force of friction can occur with what? We got sliding objects, water, air, and all of the above. What's the answer? Raise your hand if you think you have the answer. Amy? Okay, we just discussed that they are, that two solid objects sliding against one another can create friction. But what else? Can you conceivably get friction in air or water? Are there any swimmers in the class? When you guys swim, I know you guys have swam, maybe not competitively, but when you swim, you try to keep your body as aerodynamic in the water as you can, right?
It's like water resistance friction.
Yes, water creates friction. And to be a competitive swimmer, you spend a lot of your career trying to perfect your technique to reduce the amount of friction caused by water. Like you got to tuck your chin, you got to keep your body really aerodynamic, as well as car designs. You guys know that cars are tested in wind tunnels. Why did they do that? Why do they test cars in wind tunnels?
Air friction.
Air friction. That's why cars are shaped like teardrops, because they're trying to reduce air friction. So the answer is all of the above. Just because it's not solid doesn't mean that you're going to get friction, not get friction. It's whenever objects are touching one another, matter touches one another and moves by one another, you create friction. Okay? Let's look at this one really quick. When Sanjay pushes a refrigerator across the kitchen floor at constant speed, the force of friction between the refrigerator and the floor is what? What's the best answer here? Anika, what do you think? And loud enough for the class to hear?
See?
C. And that's perfect. Okay, just like with this chair. I used this example here where I was moving the chair at constant velocity. It must be enough to oppose the friction, but only just enough to oppose the friction. Then you can keep it in equilibrium, in motion, dynamic equilibrium. It must be. All right, let's try another one. This one's actually kind of fun, a little bit more of a real world problem. A 300-kilogram bear is grasping a tree, and bears do this. They climb up a tree. The way they get down is not head first. They have to go down with their rump first because they're so top heavy. So they slide down the tree, but they don't want to just drop down the tree fast. So it uses the friction. The bear will use friction on the tree. And the friction force between the tree and the bear is what? If it's a 300 kilogram bear, what do you think the friction force between the tree and the bear is? Well, let's draw it out. At your table and see if you can figure this problem out. I'm going to draw the tree. I'm going to do a really quick drawing of a bear. Here's my bear. And as you know, bears have very strong limbs. Okay, so there's my bear hugging the tree. I know, it's cute, isn't it? Okay, my bear's hugging the tree. Now recall, if you guys recall, bears, this is a big bear, by the way. This bear is 300 kilograms. That's like over 600 pounds. And bears have very strong limbs and long claws and lots of fur, so it's pretty easy for the bear to grip the tree. Now, here's the thing I want to know. If the bear is 300 kilograms, what is the force acting on the bear, pulling it down? How do we find the force again? What's the equation? F equals ma. What's the mass of the bear? 300 kilograms. What is the acceleration on the bear? It's in the gravitational field of Earth. What would be acceleration on the bear? A sub g is 10 meters per second squared. So I'm going to take 300 and I'm going to multiply it by 10 meters per second squared. What's 10 times 300? 3,000. So the force of the weight of the bear is 3,000 newtons. So that's pulling down on the bear. But the bear is only moving slowly down the tree. Or it's just hugging the tree and saying, oh, I don't know if I want to come down the tree. So what must be the force of friction? At least, if it's going down at constant velocity, what must be the force of friction? Jim? 3,000. The two are equal and opposite. So the bear's moving down the tree at constant velocity. All right, well, guys, what you just found for the bear is called weight. That's how we find our weight. Write down your mass. Everyone knows their mass. Write down your body mass on a piece of paper or in your notebook. What is your body mass? I'll tell you mine. Mine's 72 kilograms. My mass is 72 kilograms. I checked on the scale a couple days ago. Okay, mass is different than weight. Does anyone know why the two are different? Discuss that with your table. Really quick. What's the difference between weight and mass? We talked about that in chemistry. About mass. What's the difference between weight and mass? Mass is, that was your volume. Nope. Mass is regardless of any force. Mass is just a measure of what? In chemistry, we talked about it. Think about that for a second. What's mass, guys? The amount of matter, right? Mass is a measure of the amount of matter. Does it change if you're on Earth as opposed to Mars, the planet Mars? Does your mass change? No, it doesn't matter where you are, anywhere in space, mass is always going to be the same. So, it's weight that changes, because weight is a measure of the gravitational force on your mass And when you put those two together, you get the force of weight. So remember, F sub W is the mass of the object times the acceleration due to gravity. So if I'm 72 kilograms, I can find my weight really easily in newtons. All I have to do is take 72 kilograms and multiply it by 10 meters per second squared, and I get 720 newtons. I weigh 720 newtons on Earth. Would I be weighing the same on the moon? Well, if the moon's gravitational field is like 4.6 meters per second squared, I'd be much lighter on the moon. That's why on the moon, you can jump like an Olympic jumper, probably better than an Olympic jumper, because there's no gravity, or there's less gravity than here on Earth. Okay? So, on this slide, you'll notice that the difference between mass and weight. Weight is the force upon an object due to gravity. Mass is just the quantity of matter. Second law, the definition that you need to know and memorize is right here. Remember, first law was the law of inertia. The second law is the law of acceleration. And it states simply this, and again, this needs to be memorized by you because I might ask for the definition on a quiz. The acceleration produced by a net force on an object is directly proportional to the net force. And it is in the same direction as a net force, and is inversely proportional to the mass of the object. The heavier the object, the less acceleration. Okay? The lighter the object, the more acceleration with the same force. Okay? How would you like to play this game with Andrew? You know Big Andrew in my other class? We were making fun of this because we were imagining that this kid here is Andrew and this is David. Have you ever seen David try to wrestle Andrew in class? It's pretty hilarious. Andrew just does that and David's like a mosquito. But you know what? This guy, he's really aggressive. He thinks he's going to knock this big guy down, and guess what happens? He bounces into him and flies off of him. Why is that? Why is he flying off of him? And the answer is quite simply that the mass of this guy is much bigger than the mass of this guy. So even though he's applying a force of his body on this big guy, he's only going to move and accelerate a tiny bit. But it's certainly felt by that guy, right? They're both colliding. One accelerates a lot more because the one guy's lighter than the other guy. It has less mass. Okay? So next time you go and try to tackle Andrew, keep this in mind. Right, Ian? You may be a fast runner. You can just come right up and you think you can take him down, but he's not going to budge. He's not going to accelerate because his mass is much greater than yours.